Molecular orbital theory is another way of explaining what happens when bonds form. And rather than assuming atomic orbitals and kind of changing them around like valence bond theory does to modified or hybridized orbitals, molecular orbital theory actually truly considers the wave mechanics, the actual equations that produce the electron waves, just as for an atom, except for with a two-atom situation. So the parameters of the equation that describes the wave will change now, because instead of having a one nucleus influence on every electron, there's a two nucleus influence, or maybe a three nucleus, or in the case of metals bonding, which we're going to see later on when we study solids, many nuclei are in the region that cause the wave to take the form that it does. So obviously the mathematics of this are quite complicated. We're not going to get into them. What we're going to do is just kind of take the results of the theory and just scratch the surface to just get a brief overview of what molecular orbital theory results give us. So molecular orbitals are like analogs to atomic orbitals in atoms, except for they're not shaped the same. You don't have P's and S's that are spherical or dumbbell shaped, and you don't have those D's that are like four clover leaves or a donut and something that looks like a pea. They're not like that. They're completely different. But the idea is based on the same concept, that electrons behave like waves. And so there's a wave mechanics, or the kind of mathematics that should predict how the orbitals come out. Like atomic orbitals, they fill according to the Aufbau principle and Hund's rule. And so we can translate some of the stuff over from atomic theory and make use of it here. So the molecular orbitals result from the interference of the matter waves of the two shared electrons that fill that orbital. Now, interference can happen in two ways when you have two waves. One way that you can think about it is, imagine that you have like a water wave. If you could add that up to another water wave, that would interfere with another water wave that's exactly in phase with it, so that the crest of the wave and the trough of the wave exactly line up like we see here. Well, the result of that is you're going to have a water wave that's just like the previous two, except twice as big. That's called constructive interference. But a different situation would arise if the two water waves met each other when they were exactly out of phase. So here's one, here's the other one, there's their 0 points. When this one has a crest, the other one has a trough. When this one has a trough, the other one has a crest. And so because they're exactly out of phase, the net result when you add these two together is a flat spot. They cancel each other out. Those two waves just sort of dampen each other out. And the interference of these two waves results in no disturbance at all. That happens with these electron waves, and we get the same two possible results. So constructive interference for matter waves, for electron waves in a shared pair, means that the electron density increases between the nuclei. This results in what we call a bonding orbital. So this is an example of two s orbital electrons interfering with each other, and this is sort of the shape of the new orbital. So there would be a nucleus here and there would be a nucleus here. When the two nuclei are present, this is the new orbital. We've seen something that looks kind of like this when we were talking about valence bond theory. And so there are some similarities in the shape that you see, only this starts out from a whole different premise, that you're going to actually calculate this from scratch. And not surprisingly, you come up with the same result. Destructive interference is when the waves interfere so that they cancel each other out. The electron density in these cases decreases between the nuclei, and the result is what we call an anti-bonding orbital. So this is where a bond would not be likely to form. So a nucleus here and a nucleus here, and then the two s orbitals interfere with each other, and now you can see that in the zone between the two, there isn't probability of finding the electron, and so a bond wouldn't form in that case. Now, just like atomic orbitals exist in these energy levels, molecular orbitals do as well. So we get a new energy level diagram. Only this shows two different situations. On the outsides, we have the unbonded atomic orbitals. So this is a 1s level. And this is also a 1s level, but for the other atom. In the middle, we show the bonding situation. This is the interference. Well, you have two possible levels. One of them we call a sigma 1s, and that is a bonding orbital. It's lower energy than the atomic orbitals, and so electrons will prefer to be in that level. The upper one, the one that's higher than the unbonded 1s orbitals, is called sigma star 1s, and this is an anti-bonding orbital. So this is a bonding down here. The higher energy situation is an anti-bonding molecular orbital. Orbital in a sublevel, and orbital in another sublevel there. That was for a first period. In the second period, you have P's available. And so this is a picture of what bonding and anti-bonding orbitals might look like when P's are involved. So here's off-axis overlap. We have two P orbitals overlapping in two possible situations. Constructive interference results in this bonding orbital set that looks like, a pair of hot dogs. That's what the regions of electron density are like, that are off the axis of the bond. So here's a nucleus here, here's the axis of the bond, and then off axis we have these bonding orbitals. And then anti-bonding orbitals looks like this. Nucleus here, here's the axis of the bond, and then you have these regions that show in the middle here very little electron density, so bonds don't form. And then there's on-axis bonding as well. So here are two P orbitals interfering with each other. In the bonding situation, we get what we saw when we examined F2, for example, in valence bond theory. The electron probability density increases in here, decreases on the outside. So like here's a nucleus here, nucleus here, and so a bond forms. But the anti-bonding situation, here's nuclei again, shows that the probability density for finding an electron is on the outside higher than on the inside. And so there's very little likelihood of finding the electron here, and so no bond forms. So off-axis we have bonding orbitals that are called pi and anti-bonding orbitals that are called pi stars. And on-axis we have sigmas and sigma stars. So here's the energy level diagram. The 2s situation looks very much like what we saw for first period elements. There's a bonding sigma 2s and an anti-bonding sigma star 2s. And then the P's can form a bunch of different possibilities. This sublevel is a sigma 2p, and that's a bonding on-axis molecular orbital. And then the off-axis situation, if this is like on the x-axis, then you're going to have a y and you're going to have a z that can form bonding off-axis orbitals. So here's a possibility, and here's a possibility. So that's a pi 2p and another pi 2p bonding orbital. Higher energy than that is anti-bonding, pi 2p, so that's an off-axis anti-bonding orbital set. And then you've got up here at the very top a sigma star 2p, so that's the anti-bonding on-axis situation. So these are actually all molecular orbitals represented by the parentheses that I have here. And every one of them can contain up to 2 electrons. And they fill according to the Aufbau principle, and they fill according to Hund's rule. Now, we can use a diagram like this to help us figure out what kind of bonding is likely to occur. Single bond, triple bond, or double bond. What bonds form is given by a concept called bond order. Here's how bond order is calculated. Bond order is equal to the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals divided by 2. So let's ask ourselves a couple of questions here that might explain something that you may have been wondering about for a long time. What is the bond order of an H2 and what is the bond order of an HE2? Now this is first period, so let's look at the first period energy diagram. Here we've got the unbonded, like hydrogen, the first hydrogen, 1s, and here's the second hydrogen atom, also has a 1s. Each one has one electron in it. So there's unbonded orbital situation. Now I'm going to draw the energy level diagram for when they get together. We've got a bonding orbital. This is the sigma 1s, and actually much higher, we have a sigma star 1s, and this is an antibonding orbital. So we have two situations there. Now I take my two electrons, and according to Aufbau principle and Hund's rule, I'm just going to put them in the middle now in where the molecular orbitals are. So I've got two electrons. Here's where they go, right there. So what's the bond order? Well, for hydrogen, which is what we've just done here, the bond order is two electrons in a bonding sigma 1s minus no electrons in the sigma star 1s divided by 2. Well, that's equal to 1. And here's what that means. Hydrogen as an H2 molecule makes a single bond. A bond order of 1 means it's a single bond. Now let's look at helium. I'm going to put helium's electrons in here in yellow. So in addition to the one electron that hydrogen had, helium is going to have a second electron in each of its two unbonded 1s orbitals. So that means when we put the two helium atoms together, we've got 4 electrons we have to stack into this diagram. So the first two go down here, but we have 2 more, and they have to go up in this higher energy level, in this antibonding sigma star 1s sublevel. So what is the bond order for helium? Well, we have 2 electrons in this bonding sigma 1s minus 2 electrons in the antibonding sigma star 1s. And then we divide by 2 to calculate the bond order. So 2 minus 2 is 0, so obviously the bond order is 0. So that means a helium 2 has a 0 bond. In other words, it doesn't form a bond. And we know that hydrogen's diatomic, and we know that helium isn't. Here's why. Now let's go back to the energy level diagram for the second period, and we'll do all of the second period elements and figure out what the bond orders between diatomic versions of boron, carbon, nitrogen, oxygen, fluorine, neon would be. So starting out with boron. Boron, as an unbonded atom, has got 3 electrons in its valence shell. 2 of them go in a 2s sublevel, like that, and then the 2p, which has 3 orbitals, remember, contains the third one. Same thing for the other boron, which we're going to draw on the other side of the bonded inside diagram. So 2s there, and then 1 2p electron goes in one of these orbitals. So if you put the 2 together, we're going to have the electron waves of 3 plus 3, or 6 electrons going into this structure. So for boron, first 2 electrons go down there, second 2 go up here in this antibonding orbital, and then the third 2, 5 and 6, go right there. So what's the bond order? Well, in bonding orbitals, which includes the sigma 2p and the sigma 2s, I've got 4 electrons. In antibonding orbitals, the sigma star 2s, I've got 2 electrons. 4 minus 2 is 2, divided by 2 is 1. So our bond order for a B2 is 1, and that means when boron bonds to another boron, it could make a diatomic B2. Let's look at C2. What would the bonding be like if a C2 molecule formed? Well, let's draw individual carbon unbonded first. It's 2s2, 2p2. So there's the 2s orbital, and then 2p sublevel's got 3 orbitals in it, and I would have 2 electrons in separate orbitals. The other carbon would look just the same, so I'll draw that. And if we add up the total number of electrons, we have 4 in each carbon, so that means we're going to put 8 together in the energy level diagram for the molecular orbitals. So the first 2 are going to go down here in this sigma 2s bonding orbital. The next two have to go in the sigma star 2s antibonding orbital. Next, two more in the sigma 2p bonding orbital. And then we have two pi 2p bonding orbitals. So this is maybe on the y-axis and maybe this is on the z-axis, where this was on the x-axis. So one orbital each, and according to Hund's rule, one electron is going to go in each of those. All right, so what's our bond order? Well, the bond order is number of electrons in bonding orbitals, which is 1, 2, 3, 4, 5, 6, minus the number that's in antibonding orbitals, and that's just these two, divided by 2. So 6 minus 2 is 4, 4 divided by 2 is 2, so that means a carbon diatomic would be double bonded. Let's look at N2. Now here's a molecule we're familiar with. Let's see if we get the same result that we would when we've done it with Lewis structures, for example, as a predicting tool. So nitrogen is 2s2, 2p3. So I'll put 2 electrons in the 2s, and my 2p in the unbonded state is going to have 1 electron in each of the 3 orbitals. The other nitrogen will be identical to that, and 2s is also full. Well, each nitrogen's got 5 electrons, so when we put them together, that means 10. Let's stack them into the molecular orbital diagram. 2 here, 2 here, that's 4. 2 more make 6, 8, 10. All right, how many do we have in bonding orbitals? 2, 4, 6, 8 of them. So our bond order is 8 minus the number that are in antibonding orbitals. Well, that's these two. And then we divide by 2. Well, 8 minus 2 is 6. 6 divided by 2 is 3. So that means nitrogen, when it's diatomic, has a triple bond. That matches what we already know. So molecular orbital theory explains stuff that we know, and later on we're going to find out that it explains stuff that we don't have an explanation for with the theories that we've learned so far. Now let's look at oxygen, O2. What's the bond order? Well, I'm not going to do the individual atoms, but you know that there are going to be 6 electrons over here and 6 electrons over here, because that's the number of electrons that are in oxygen's valence shell. So let's put 12 total electrons in the molecular orbital energy diagram. First 2 go down here in a bonding orbital. Next 2 in antibonding. That's 4, 6, 8, 10, 12. What's the bond order? Well, if we count up the number of electrons that are in bonding orbitals, we have 2, 4, 6, 8, just like we did for nitrogen. Subtract the number that are in antibonding orbitals. Well, I've got these two, and then that pair. So that's a total of 4. And then I divide by 2 to get my bond order. So 8 minus 4 is 4. 4 divided by 2 is 2. So that means the bond order of an O2 molecule is 2. In other words, oxygen double bonds to itself. Again, just like with the nitrogen example, we knew that. Molecular orbital theory explains what we know. Now let's work on F2, fluorine. So fluorine's a column 7. That means each of the fluorines is going to have 7 electrons in the unbonded state. So that means when we make the molecule, we have 14 valence electrons to put in the energy level diagram. First 2 there, second 2 there, 5 and 6, 7, 8, 9, 10, 11, 12, 13, 14. What's our bond order? Well, the number in bonding orbitals is 2, 4, 6, 8. The number in antibonding orbitals is now 2, 4, 6. 8 minus 6 is 2, divided by 2 is 1. So that means when fluorine makes a diatomic molecule, it's single bonded. Now let's go to the last one in the row, and then we'll be done with this. Neon. Well, each neon has got 8 electrons, full octet. So our energy level diagram should get 16 total. Here they are. 2, 4, 6, 8, 10, 12, 14, 16. What's our bond order? In bonding orbitals, we have 2, 4, 6, 8. In antibonding orbitals, we have 2, 4, 6, 8 as well. So our bond order is 8 minus 8 divided by 2, which is 0, which means a neon diatomic doesn't exist. And we knew that. So we can see that molecular orbital theory explains stuff that we already had a different explanation for. But molecular orbital theory also explains things we didn't have a good explanation for, like resonance, for example. Nitrate, if you recall, has these 3 possibilities for its structure. You can have a double bond to an oxygen in 3 different locations. And so we have said in the past that this is a resonance structure, and that means that that bond is actually switching back and forth, switching back and forth, switching back and forth. But we don't know why. We don't have any good reason to believe that it would do that, other than the fact that experiments show that the bond is more stable than a single bond would be. Well, MO theory, if you could do it for this structure, it's a little more complicated than the diatomics that we were looking at, you would find out that the bond order for each of these 3 bonds is actually 1 and 1/3. And so it isn't really a single bond, double bond. It's a 1 and 1/3 bond, 1 and 1/3 bond, 1 and 1/3 bond. The pi bond in the molecular orbital theory is said to be a delocalized bond. In other words, it's not locked into any 2 of the atoms that are bonded. As a picture, this is what it looks like. Those orbitals overlap, if you will, in such a way, according to MO theory, that they form this new bonded orbital that looks sort of like this. It's 2 of these little flying wing things off axis of the sigma bonds that bond the nitrogens and oxygens together. And so that second pair of electrons that forms the pi bond is actually delocalized, and it's moving all around in this shape of an orbital. And that's why we have a bond that's more stable than a single bond, double bond situation, because we really have 1 and 1/3 bond order, and so those electrons are floating around all over the place. Another example is benzene. Benzene is a great example of something that shows delocalization. Here is a sigma bond structure. If you're looking at benzene like a aerial view, looking right down on the benzene ring, you've got the sigma bonds here, 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 and here, and then you've got sigma bonds going off to the H's. But this is sp2 hybridized orbital if you use valence bond theory, and that means we've got a p orbital going up and down, into and out of the screen here, and here, and here, and here, and here, and here. And so we could have like maybe overlap here and get a pi bond, overlap here and get a pi bond, overlap here and get a pi bond, and then we could explain it. But what doesn't get explained is the fact that resonance exists, and we really don't have double bond, single bond, double bond, single bond, double bond, single bond. We really have bond orders of 1 and 1/2 all around in this structure. So the 3 pi bonds are really 3 delocalized pairs of electrons that are shared by everything in the ring. So this is a picture of that. There's the sigma bond structure that's shown by the lines there. And then above and below it, we have this double toroid shape that represents those 3 extra electron pairs that aren't making double bonds in 3 different locations. They're making 1 and 1/2 bonds in all 6 locations. And that makes this a much more stable molecule than if you could break single bonds in any of 3 places and tear the thing apart. And so benzene is very stable. So MO theory is the best theory that we've got for explaining bonding. Unfortunately, it's the most complicated theory as well, and some of you are probably still shaking your head wondering, what is he talking about? Don't worry too much about it if you're just concerned about the AP exam, because the AP exam doesn't really cover MO theory. But I think an introduction to MO theory helps us better understand some of the less advanced theories like valence bond theory and VSEPR theory that we've been using, and gives us a way to explain resonance, which we haven't had up to this point. Well, that's it for bonding. Now we're going to start moving into areas where we start to look at not the attractions between atoms inside of a molecule, but the attractions for one molecule from another molecule, so between molecules. And that explains some of the physical properties that we see. So far we've just been explaining chemical properties, but physical properties are also an important part of chemistry, and that's explained by something called intermolecular forces. So that's the area we're going to be moving into next.